Alright, so yesterday we talked a little bit more about our random number generator, not a dice kit, and the fact that we need to be able to count. And in digital electronics, we talked about kind of the definition of digital was that everything was either 0 or 5 volts. A 0 or a logical 1, right? Everything is a 0 or a 1. Whether it be information, whether it be music, video, whatever, everything breaks down to zeros and ones. Okay? So in order to count, we have to count in zeros and ones. Okay? There is no such thing as a 2 in digital electronics. Okay? There's things we can represent. We can try and, have a code that represents 2. Okay? But there is no such thing as a 2 in digital electronics. Okay? So today we're going to talk about number systems. And I'm going to start with a number system that I hope you're very familiar with, and that's the decimal number system. Okay? The decimal number system, very common, probably because we have 10 of these, right? So it made sense to count that way. So a lot of people use decimal number systems. Okay? So in a decimal number system, it's base 10. Decimal number system is base 10. What base 10 means is that you have 10 unique characters that represent numbers. Okay? You've probably seen 1 or 2 of these before. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 10 characters, right? Because 0 counts. So I have 10 characters, shapes, whatever, that represent numbers. In decimal, what happens when you run out? What do you do next? What's the next thing? Yeah. No. You add a 0, you carry a place. So I like to say, we carry a place. So then it would be 1, 0. Right? 10. And then it would be 11, and 12, and 13, and 14, 15, 16, 17, 18, 19. And again, I've run out, so I'd carry a place. 20, 21, 22, 23. You get all the way up to 99. I run out, I carry a place to 100. Okay? So that's the system that we're all pretty familiar with. I hope. Okay? Is the decimal system. Now, in theory, there can be any base number system. There could be a base 2 number system, base 12 number system, a base 38 number system. There can be really any base that we want. It's just how many characters do we have, how many states do we have to describe a number. And in binary, in digital, right, we only have 2. So binary is base 2. We only have 2 states. That's it. We don't have 10 states. We only have 2. That's it. So, we're going to start same as decimal with a 0. And then a 1. So far so good. Except now I've run out of characters. Right? That was it. I only have 2 characters. 0 and 1. That was it. I only have 2 characters. In the decimal system, what did I do when I ran out of numbers? Carried a place, right? So in the binary system, what am I going to do when I run out of numbers? I'm going to carry a place. Okay? I'm going to carry a place. So 0, 1, 1, 0. Now, first things first, don't get yourself into the habit of calling this 10. Right? We're kind of in the use that would be like a 10, right? But you need to get in the habit, especially as these binary numbers get bigger and bigger and bigger. You're going to try 1,111,000. No, just 1, 0. 1, 0. Okay? Then I can go 1, 1. That's cool. But now I've run out of numbers again. Right? That's every combination I could have had there. So I got to carry a place. 1, 0, 0. I got to carry a place. And then 1, 0, 1, 1, 1, 0, 1, 1, 1. I'm out again. That's all my possible combinations. 1, 0, 0, 0. 1, Okay? Now, one thing you're probably going to notice right away is that binary numbers get large quickly. Just visibly large. They get large quickly. It is the same number. This is that. They're the same. This is that. This is that. They're the same number. They're just kind of physically large. Okay? But the beauty part is I can then express any number I want using digital. Using only ones or zeros. Okay? Now, visually, I'm going to fill in just some initial zeros. These don't change the value or anything. They just make it a little easier to compare. Initial zeros, these don't change the value. Okay? I don't require you to turn, turn in something and you say 1. I won't be like, what? Why isn't it 0, 0, 0, 1? That's fine. I don't require you to turn in something and you say. Now, anybody notice anything about the pattern here? Anybody notice a pattern? Anybody notice anything about the pattern here? Yeah.
It's like.
You notice the pattern?
Looks like it's like diagonal.
Like this is kind of filling in?
Yeah.
Yeah?
And then it's like, yeah.
Yeah. Yeah. It gets exponentially larger. True.
It gets
2 to the n, right?
Yeah. As long as there's also.
It gets exponentially larger. True.
There's 1 and then there's 2
to the n, right? Yeah. Yeah. Yeah.
Do you know what this reminds me of?
I don't.
It reminds me of what's the name of that graph where it's x squared or whatever?
Oh, like a logarithmic graph or something.
Yeah.
So here, check out my pattern here. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Here, right? And this one is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. This one's 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. And over here, 1, 2, 3, 4, 5, 6, 7, 8 zeros. What would the next number be? What do you think? What would the next number in this first column be?
1.
1. What would the next number here be?
1.
1. How about here?
0.
0. How about here? 1. Okay. So, in theory, I don't even need to know what the number represents to count in binary. Because if I just follow this pattern, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0. If I just follow this pattern, I can make, an infinitely large chart. And in theory, I'd always be counting in order in binary. Which is pretty neat. Now, this is nice. And to be honest, by the end of this class, I would expect that you'll be pretty good at just sort of seeing the numbers, 0 to 12. You're going to be pretty good at seeing those numbers 0 to 12, 0 to 16 pretty quickly. Okay? Now, if I asked you to tell me, and you might see like in the end of course assessment, you might see the number 235 in decimal, convert that to binary. Now, all right, so I guess in theory, you could make a 235 row chart, or 236 row chart. But that would be time consuming, to say the least. Right? So there must be a better way. Must be a better way for us to do these conversions. So I'd like to show you 2 little shortcuts for converting between binary and decimal, sort of make your life easier. Okay? So, the first thing I'm going to show you is called weighted multiplication. So weighted multiplication it takes a little bit of setup. You got to set something up. This chart thing. I used to call it the chart method before I knew what it was called. It's called weighted multiplication. So you have to set up this chart, and that's like the most time-consuming part. After that, it's pretty easy. So the way I set up the chart is base to the power of a number. So right now I wrote x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, x to the 5, x to the 6, x to the 7, x to the 8. We'll stop there. Okay, so that's how I start the chart. X to the every x point. And you'll notice I started at 0 here and went it went up this way, that's kind of important. It's kind of important to set it up that way. Now, why did I use x's? Well, x is the base. Now, why did I use x's? Okay? X is the base. So, what base am I working with right now? X is the base. Which is what? What are we talking about? So, what base am I working with?
Binary fusion.
Binary is 2, yeah? Base 2. That's the base I'm working with right now. The cool thing about weighted multiplication, what I'm going to show you, is that when we talk about hexadecimal later, which is base 16, right? Or octal, which is base 8, or whatever the heck you want to work with, this system works with any of them. And it's exactly the same, so it's nice. So you learn it once, and then you can apply it to anything else. So that's why I put that in there. But now let's put in our base. Our base is 2. That's what we're talking about today. So our base is 2, so 2 to the 0. Let me scoot that up. That's just talking about today. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 4. Sorry, 2 to the 3, 2 to the 4. Just making sure you're paying attention. 2 to the 5, 2 to the 6, 7, 2 to the 8. All right. So what's 2 to the 0?
1.
It's a 1. I asked a math teacher over the summer. I said, "Why is that?" What's 2 to 0? It's because it is. I'm like, okay, that's what I tell people too. 2 to the 0, anything to a 0 is a 1. Okay? I don't know. 2 to the 1 is a 2. 2 to the 2, 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. Times 2 is 64. 128. Times 2 is 256. Those number patterns look familiar? No. We're seeing 4s and 8s and 16, 32, 64, 128. Okay? That 2 to the n pattern we talked about before, you see that all over. Anything electronic. You know, my phone has 32 gigabytes of storage. Or I can buy 16, or I can buy a 64. You know, my phone has 32. The Nintendo 64, my 8-bit NES. You always see these numbers. Okay? It's 2 to the n pattern. Nintendo 64, my 8-bit Alright, so now my chart is done. That's the setup part. And like I said, it takes a little while. It won't take you that long because you won't be talking to people through it, right? But you set up your chart. Powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. As far as you need. This is going to be plenty for us. Powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. As far as you need. That was enough. If we had like a really mega huge number, we might have to go further. This is going to top out at 512. That was enough. If I wanted to convert like 3,000,001, I'd need more columns. This is going to top out at 512. So, how do I use weighted multiplication? Well, first, let's use it. It's easier to start going binary to decimal. So, I need a binary number. Let's go 0, 0, 1, 1, 0, 1, 1, 0, 1. Full disclosure, I have no idea what that number is. Just made it up as I was going along. Okay? I don't know what that is. Now, I want to be able to convert that thing to decimal. Whatever that is, I want to know what it is in decimal. Now, I want to be able to convert that thing. So this is how this works. This is how this weighted multiplication works. I want to know what it is in decimal. I'm going to have 1. So this is how this works. 64. So I write 64 down here. I'm going to have 132. So plus 32. No 16s. I'm going to have 1 8. So plus 32. 1 4. No 16s. No 2s. And 1 1. So any place there's a 1 in that column, you're going to add that quantity. 64, 32, whatever it is. Okay? So, let's see. That would be 13, 15, 45, 109. Somebody back that up for me. Yeah? So if I add those together, I'd see 109. And that's what it would be in decimal. Okay, so that's your kind of quick conversion method. It takes a little while to set up that chart, but if you were on a quiz or something like that, you know, you just, before you start, you set up your chart, and then you can use it again and again. Yeah. Or something like that, you know, you just, before you start. I'm going to write one up here I'd like you to try on your own. Yeah. Let's see, how about 1, 0, 0, 1, 0, 0, 1, 0, 1. Let's see. You guys try on your own. See if you can figure out what that number would be in decimal. You guys try on your own. See if you can figure out what that number would be in decimal.
Where's that from? Is that a video game?
Don't feel ashamed if you need to use a calculator to do some of these additions. It's totally fine. Don't be embarrassed. I do it all the time. Double check myself.
Where was that song from?
That was Girl from Ipanema. What's it from? I don't know. It's very popular. Double check myself. Yes. 1, 0, 0. 1, 0, 0. 1, 0, 1.
So like, is there any kind of combination that would give you a number?
No. No, I'll give you a number.
Really?
Yep. Yep. That's why it's nice as a teacher, because I can just randomly write stuff up there and it works out. Yep. Let's take another 30 seconds or so. I can just randomly write stuff up there and it works out.
Why is origin on these
Let's take another 30 seconds or so.
Anarchy is reading the same thing the origin and vice versa. Maybe she's really not going the properties and change
All right. Now, I have not done any of the math here to figure this out, but I will tell you one thing right now. The answer you have had better be an odd number. I have not done any of the math here. Okay? This is not because I am clairvoyant. Okay? The answer you have had better be an odd number. Right, it might be, but that's not how I know this. Okay? Not because I'm all of these numbers are even. That's not how I know this. The only way to get an odd number is if this guy over here is a 1. That's the only possible way. Sometimes that's called the parity bit, right? Or the sign, parity bit. So then it knows, if I look at that immediately, I know if the number's even or odd. If that was a 0, I'd say the number's got to be even. But it's a 1, so I know the number's got to be odd. Okay? So I'm looking at 256 plus 32. So that's 288. Let's see, plus a 4, 292. Plus a 1, 293. How does that work? Yeah? Is that okay? Plus a 1. Okay, cool. So this is how I convert from binary to decimal. But I can go the other way. Let's say I want to go from decimal to binary. I can do the same thing with weighted multiplication. And I'm going to show you a different method too after this. Whichever one you like, you should use. Okay? But let's say a number less than 512.
413.
Fantastic. 413 base 10. What is that in binary? Okay, so we're doing the same process. We're just sort of doing it in reverse. So I'd say, is 256 less than 413? Yeah, so I'll take one of those. So now 413 minus 256, what's left over? Yeah, so I'll take one of those. 157 is 128 less than 157? Yeah. I'll take a 128. Yes, please. Minus 128 is 128 less than that 29?
Yes.
I'll take a 129. Okay. Now, is 64 less than 29?
No.
No. No. So I can't have any 64s. 32 is not less than, I can't use any 32s either. It's too much. Put me over. So I can't. Alright? 16 though, I can use a 16. So I'll take 116. Put me over. Please. Okay? So 29 minus 16 is 13. Is that right? Okay. 13, can I take an 8? Yes, please. 13 minus 8.
Whoa.
is 5. Yeah, I'll take a 4 as well. 4 is less than 5. 5. Yeah. Now 2 is not less than 1, so no 2s. But I will take a 1. So my number 413 in binary is 11001110. My number 413 in binary is, and then I say base 2. Just so no one thinks I'm talking about 110,011,101. Yes. Just so no one thinks I'm talking about. Okay.
The 413, there's a 10 below it.
110. So that means it's a decimal number. I'm just telling you that 413 is decimal.
And so we take that number and put it against the numbers in charge.
So that means it's
Yes.
decimal.
What binary?
I'm just telling you that. Yes. Yeah, this is to convert that number to binary. Now I will show you another method. This is a way to use weighted multiplication. The nice thing about this method is that you set up the chart, you can go either direction. Okay? That's weighted multiplication. Now I will show you one other way to convert from decimal to binary. Okay? That's weighted multiplication. Now I will show you one other way to convert from decimal.
No idea.
Okay.
45.
Yeah.
45.
Five.
Do
Fantastic.
we still get a 5 minutes though?
No, we won't. Fantastic. All right. The other method I'm going to show you is called successive division. Now, successive division basically only works one direction. It goes from decimal to our base. Okay? So decimal to binary in this case. Basically only works one direction. Okay? That's the only way it works. So, I'm going to start with my decimal number. In fact, I'm going to use the same decimal number that we just did, just so we can check it, make sure it still works. So that was 413. I'm going to start with my decimal number. In fact, I'm going to use the same decimal number. Okay. So 413 is my successive division number. Okay. So that was 413. So I'm going to divide that. Okay. So 413. I'm going to divide that by the base. So I'm going to divide 413 by the base. What's the base? 2. Divide that. So by the base. What's 413 divided by 2? Divide 413 by the base. All right. So max is 206.5. And I'm with you, but you're a little too advanced for me. We need to go back to like
207.
3rd grade maybe. And we need to say
413.
206 remainder 1. Like remainder?
Remainder 1.
Where's our remainder? Remainder, what's that? Yeah, remember we had remainders way back before we had decimals? So remainder 1. Okay, now, check this out. 206 divided by 2. 103, remainder what? 2. Now, check this out. 206 divided by 2. Remainder 0. 103. 206 divided by 2 divides evenly. There is no remainder. Okay? What's 103 divided by 2? 206 divided by 2 divides evenly. There is no remainder. 51. Okay? What's remainder 1? Okay? 51. 51 times 2 would be 102. So remainder 1. 51 divided by 2. 25. 2 would be 102. Remainder 1. Again, please don't feel like you have to do these in your head.
Oh my God.
You absolutely can do these. You can do these with the calculator. It's fine. 25 divided by 2. Again, please don't feel like you have to do these in your head. 12. Absolutely can do these. Remainder 1. 12 divided by 2. 6. Remainder 0. 6 divided by 2. 3. Remainder 0. 3 divided by 2.
How'd you remainder on the time?
It's just a 0.
Oh, never mind, okay.
3 divided by 2.
1 remaining 1.
Thank you. I was a little concerned that it was taking a while. What's 1 divided by 2?
0.
Oh, yeah. Almost always people say a half, 0.5. I don't know. 1 divided by 2 is 0. Remainder 1. When you get to 0, you know you're done. I don't know. And not before. Okay, you have to get all the way to 0. Now, what do we do with this information? This is the trickiest part. The part that you see people get wrong the most. I read it that way. What do we do with this information? This is the trickiest part. 1 1 0 0. I read it 1 1 1 that way. 0 1. 1 1 0 0 1 1 1. It's the same number. 0 1. It works. Okay? Now, which one's better? Weighted multiplication or successive division? It's the same number. It works. Yeah. It doesn't really matter, right? Whatever you prefer. Some people like division better. Some people like subtraction better. Some people like that they set up the chart once and then they have both. Whatever. It doesn't matter. Mathematically they're the same. No big deal. They both work on any base. So when we start talking about other bases, both methods will work. It's fine. Right, bless you. They both work on any base. So when we start talking about other bases, both methods. That is successive division. All right. Now, kind of an interesting byproduct of this 2 to the n thing. To give you a little background. So, when computing was in its, I don't want to say infancy, but teen years perhaps, okay, things were quite a bit smaller. Computing was in its, our first computers had kilobytes of memory, right, or bytes of memory. Now a byte, B-Y-T-E, okay, is 8 ones or zeros. This is a byte right here. That's 1 byte. Okay. Now, if I have more of these, right, I can have, you know, kilobytes or megabytes or gigabytes or terabytes, right? I can have, you know. Now, what's interesting is when we were in these teens, gigabytes, terabytes, we were going up by 2 to the n. We were at 256, right? 256 bytes. And then we went to 512 bytes. And then, what's 512 times 2? 256, right? 256 bytes. Okay, so we got to there. And our computer scientists at the time said, you know what we're going to do? Instead of saying 1024 bytes all the time, we're going to say that's 1 kilobyte. You know what we're going to do? Instead of saying 1 kilobyte. Because that's easier to say, right? 1 kilobyte as opposed to 1,000 bytes. Or 1 megabyte as opposed to 1 million bytes.
Like, what do you do with that?
Because that's easier to say, right? Miriam asked an excellent question. Or 1 megabyte. 1024, though, does not equal 1,000. Right? And kilo is a metric prefix. It means 1,000 of something. We were joking the other day about 2,000 mockingbirds is 2 kilo mockingbird, right? The metric system is universal. You can use it for anything. So this runs us into a problem here. 1024 and 1,000 are not the exact same thing. But come on, 24 bytes is not really that big a deal. It's not that much. I mean, in the world of millions and billions, you know, 24 bytes is no big deal. But as we get to a megabyte, this problem compounds rather significantly. Many, 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 many more bytes are being lost to this sort of conversion. Okay? And when we get to gigabytes, which is billion, right? Now that's a pretty big difference, pretty significant difference between a billion bytes and what a gigabyte is. Now, really, it probably wouldn't matter to us. You know, it's happening at the computer level. We don't really notice until recently, as we started getting 500, you know, gigabyte hard drives and terabyte hard drives. What happened was companies that sell you hard drives, Western Digital, Seagate, Samsung, these companies, if they sell you a 1 gigabyte drive, that's pretty small, okay? But if they sell you a 1 gigabyte drive, they will sell you, if they sell you a 1 gigabyte drive, that's pretty small, exactly that many bytes. If they sell you a 1 gigabyte drive, 1 billion bytes. That's what they're going to sell you. Exactly that. Because as far as they're concerned, that's a metric prefix. So they're selling you 1 billion bytes. Now, what happens when you plug that into your computer? Because your computer will not see 1 gigabyte. It'll see about, I think it's like 870 megabytes or something. Your computer will you go, hey, 1 gigabyte. I bought a gigabyte. Where's my space? Right? Because the computer thinks a gigabyte is a larger number. Where's my space? The computer thinks the gigabyte is 1, 2, something, something, something. That's what it's looking for when the computer says gigabyte. It's a larger number. The computer thinks it's not. So your companies, your hard drive companies are like, hey, don't blame us. It's the metric system, man. Yeah, it's the metric system. So we're selling you 1 gigabyte, 1 terabyte, 5 terabytes, whatever it is. 5 terabytes to them is 5 trillion bytes. Because the metric system. When you install it on your computer's going to say, oh, no, that's not 5 terabytes. In computing land, well, it's like, 4.7 or something, whatever it works out to be. I don't know off the top of my head. So people get mad. They, fire up nasty gram emails to Western Digital and Seagate, Samsung, and all say, hey, I bought this, I expect this space. And their polite-ish response is, well, what you don't understand is, we're selling you the metric, right? This is a metric prefix. This is 5 terabytes. And your computer just recognizes it as a small amount. Now, how would you solve this problem? What's the solution, you think? Your computer just recognizes it as a small amount. Should the hard drive companies change their ways?
No, it's business.
False advertising.
What's the solution? You think it's false advertising?
Yeah.
I mean, they are selling the truth.
They are selling.
Misleading.
Misleading is fair.
Fine print.
Now, what the hard drive manufacturers have suggested instead is they say, hey, computing, you guys need to pick a different prefix because you're the ones that are wrong. That's not a kilobyte. So you need to come up with a new name. Their suggestion? Pick a different prefix because you're the ones that are wrong. Kebibyte.
What?
Megabytes.
Like,
Gabibytes.
no joke.
Their suggestion. Tebibyte.
Nope.
That's their suggestion. For better or worse, for right or wrong, they're like, you computing people, you were the ones that goofed it up. This isn't a kilobyte, so you just pick a new name for it. And so when I open up my computer in Windows, it'll say, yeah, you have 5 terabytes, but you have 4.7 tebibytes. Now, as you can imagine, people are software writers and those sorts of things. They're not super keen to rewrite all their software, say tebibytes or gabibytes or anything else. Hard drive manufacturers are kind of digging their heels in, so we have the stalemate right now. Still today, if you buy a hard drive today, you're going to get the smaller amount that you think. And if you go to their website, you'll see a big disclaimer. Hey, this is why this is. Don't come crying to us because you get less than you think you did. It's a big problem. So that's kind of an interesting thing. Yeah. Hey, this is why this is. No. Unfortunately, no.
I swear that's happening.
Well, I mean, anything's possible, I suppose. But just from the numbers, from the math perspective, no. Right? See you, buddy. So that's kind of a neat byproduct of this power of two things that we can't quite land on a million or a billion or a trillion. So we have these sort of issues that come up as a result. That's kind of a neat byproduct. Tomorrow, you're going to be working on the binary activity. We're going to do some binary. Here's my deal for you, though. I understand. I know certainly that there are calculators that can do this work for us. Okay? I know, hard to believe. In fact, pretty much every calculator, like regular calculator, whether it be a TI, graphing calculator, scientific calculator, has base conversions built in for the most common ones, typically binary, octal, and hex. Okay? Typically, it's got those on almost every calculator. Your computers, the Windows-based calculator, you can choose programmer mode, and it has the base conversions in there. Obviously, you've got the internets, and I'm sure Google will do the base conversion for us too, right? So here's my deal for you. I'm not trying to make you do busy work, but you need to do like an honor system, self-check. When you do this activity, I need you to do a couple by hand, so you're like, yeah, I got it. I know how to do it. And once you've got it and you're good, do the rest with a calculator. I don't care, it's fine.
Okay.
Okay, that's no big deal. On the end of course assessment, on our finals, you will be able to use a calculator. There's no calculator restriction. Okay, but like I said, make sure that you can do it by hand. Especially like 0 through 16, you're absolutely going to need to know a lot about. Okay? That's all I've got for you today. If you got any questions, let me know. Tomorrow will be your period to work on that activity. Especially like